Hello everyone, and welcome to the Energy Resilient Lab. Our lab is dedicated to giving you the knowledge, skills, and the encouragement that you need to become energy resilient and energy independent. Today we're moving forward with the next size in energy storage system, so that's the utility scale system. In this case, the utilities around the country now are adding a lot more resilience to help them mitigate the issues that can arise with solar and other renewables being added to the grid. So solar and wind and other renewables are not consistent all the time, and so the grid has to be able to respond to those changes throughout all time. And so the more energy storage systems that you have online, the more solar you can mitigate. So you can have an energy storage system that is a gigawatt hour of energy and 250 megawatt power. And so what that can do is it can give you 4 hours of accepting 250 megawatts. So if you put solar onto the grid and it's producing for maybe 6 hours or something, one 250 megawatt, 1 gigawatt hour system could accept all of the power from those solar arrays and then hold it for later usage. So it's the same disparity that we find in the home, where the solar is producing in the middle of the day when there's not a lot of people there. You may have a kind of a high power consumption during lunchtime if you're there cooking for a bunch of children or for yourself. Then there will be power consumption, and the solar can cover that, and you can run directly off of your renewables. But later in the day, when the solar falls off at 5 or 6 in the evening, that's usually when everyone gets home and starts using a lot of power, doing laundry, cooking, all of that stuff. And so the utility sees that and needs to be able to handle all of those conditions. And so putting in a very large scale system that's a gigawatt hour of storage and 250 megawatt of power can give them the storage that they need to capture all of the renewables and then deploy them in the evening when they're used more heavily. So that's a very common case for all different scales of energy storage systems. You're just grabbing the energy when it's less needed and moving it to when it is more needed. And that can be done in a lot of different ways, like we've talked about. We talked about home energy storage, we talked about commercial, and then here going on to utilities. So utilities can take care of their own systems, and like we talked about in the industrial commercial section, the utilities can crowdsource the energy storage and power that they need by encouraging homeowners to purchase batteries, and in some cases giving credits or free batteries for those people to add to their system. One of the things that they will take from that is they will take control when they need it to cover peak loads or to do some energy arbitrage. And so you have to take that into account when you're assessing if you want to do an energy storage system that's subsidized by a different entity. But in this case, where utilities are taking care of their own systems, there's that where you're just doing time of use, you're taking the power during the day when there's lots of renewables, and then deploying the power when it's needed more in the evening. And that can be at any scale. So there's small municipalities that have energy generation facilities, and they can be augmented with batteries. So if they add a battery system to their system, then they can peak shave or have some energy storage to just protect against high power usage times. So usually in the utilities, they have to plan a year in advance or more, and so they say we're going to be taking 100 megawatts at our peak load in August when everyone's air conditioning is on and everyone's charging their cars and other large loads. And so they plan it out, but if they have energy storage systems throughout the year, they can peak shave, just moving power if there is different time of use periods. So municipalities and other small power generation companies, utilities essentially, they have the same concerns that we do. So they have a power bill, and the power wholesalers set those prices. And so all of the prices are set, and they can use an energy storage system to move the power if that's beneficial to them. So they can get those kind of benefits throughout the year, and then during the peak time, if there is unforeseen condition where there's a very large heat waves. So we've been seeing heat waves. We had the heat dome episode a couple back. And so in that case, the utility can't really plan for that very easily. And so they just have to eat the cost. So if everyone has their air conditioning on and it goes over the peak that they planned for the year, they just have to pay the excess money to cover that. So that's kind of how it works for them. And so the more energy storage they have at their generation facility, the more margin of error they can account for these kind of peak energy consumption times. So that's one of the uses, and that one can be at the 5 megawatt scale, it can be at the 100 megawatt scale. It just depends on how big the municipality or utility is. Once you get up to the large PacifiCorps and Northwestern and kind of very large groups of utilities, they need energy storage in the 5 gigawatt hour, 1 gigawatt power. So just to give you an idea, there's some power plants here in the West that can produce a gigawatt continuous. So that's what's supplying the base load for large regions. And so you can do that with battery energy storage. So you would have a gigawatt power worth of inverters or PCSs, and then you'd have maybe 5 gigawatt hours of storage. And so what that would give you is just 5 hours at a gigawatt power. And so that can get you through very large events. So you don't have to use all the power that's available. You can keep it in storage. I mean, you can keep the energy in storage and just use the power required to clip the peak or whatever you're trying to do. The other things that the utilities need to manage is the voltage sag or voltage issues on the grid. It's usually sag. You can have high voltage conditions on the grid as well, but usually it's from overdrawing. So if you have a large battery energy storage system, you can have reactive power from the inverter injected into the grid. So there's voltage support that you can add. So with the AC phases operating, the inverter can take power on the edges in the wave, 20 millisecond per complete sinusoid. And so within the first 3 milliseconds, and then the last 3 milliseconds in a 10 millisecond section, which is the top of the wave, they can draw power from the grid into the BESS or into the capacitors, depending on the scale of how much power you're drawing. And then they can dispatch power or push amps out into the grid during the peak section. And so when they do that, it kind of pulls down the voltage on the edges and it props up the center. And so that is one of the options for power conditioning with an energy storage system. Another one is power factor correction. So that's where you're injecting power kind of in the same way, but what you're doing is you're drawing power earlier in the wave and then you're deploying it later in the wave if it's a lagging power factor, or vice versa if it's a leading power factor. And all you're doing is distributing the current over the wave. So you're just moving the current that is seen by the utility to be in sync with the voltage. So when the peak of the voltage comes around, the peak of the current also happens concurrently. When you don't have a reactive system and a system that can augment the reactive nature of your loads, then you're just at the will of the system. And so your motors are going to be operating and they're going to move the current as far as they need to operate. And so there'll usually be a between a 0.9 and a 0.8 power factor range where your system is operating if there's lots of motors. So to remedy this, the power is drawn earlier in the wave. So you just program the inverter so it will pull power early in the wave and sync it with the voltage wave. And then when the peak demand comes from the actual motors on site, the energy storage system will deploy those amps, and so the grid won't see those amps. And so the power is just lined up perfectly. So there's reactive amps and then normal amps in a system, and so you're just biasing the current and moving it to the time period to make it more stable for the grid. So that can help the grid stay more balanced. But the grid, with all of its inductance throughout its whole system with transformers and long lines of wires and the capacitance of those lines as well, they have resonant frequencies and they will have power factors as well. And so having a large energy storage system, you can have it there just watching the condition of the power and injecting current when needed to prop up the voltage or to adjust the system back to a power factor of 1. And so a power factor of 1 is when you're centered and the current is perfectly in sync with the voltage. And then you have a minus 0.8 or plus 0.8 where the current is shifted before the peak of the wave or after the peak of the wave. And so you're just adjusting the current so that the grid only sees a draw when the voltage is in sync with it. So that's kind of the reactive power options that you have with inverters. And so having those features built in is useful, but you need to know how it needs to react to fix the power. And so in most systems, there's going to be an energy management system. And the energy management system is going to take in the power measurements from the grid, and then it will use the inverter to augment the grid to correct the power factor and to boost the voltage and just support the grid in any way that it needs to be supported. And so these are a few of the systems that can be deployed at the utility level. And again, the scale, really the only difference going from a home to industrial. In a home, usually you don't have to correct for power factor. When you go to commercial, then there's going to be more issues because you have large motors and things operating. And so in that case, you may want some conditioning. So in our region, they will charge you extra for the power factors. They just add it to the peak demand charge depending on how bad your power factor is. And so in some regions, they will threaten to disconnect your power if you don't correct your power factor on site. And so that's where a battery energy storage system can help. And then so they do that as much as possible to get people to solve their problem at their industrial level. And then any other issues, so to correct for residential or for the normal oscillations of the grid, the utility can take care of that using energy storage systems. So thank you guys for making it through these series of energy storage systems, all the way down from the very small up to the utility scale. Today I'm wearing my glasses. I've just got some irritation in my eyes, so please excuse the eyeglasses in this video. But if you like them, comment on there and maybe I'll just wear them every time. Anyway, thank you guys. Have a great day. We'll see you next time.